Hi guys, I'm Zach McGill, and this is my video lab report for an object moving at constant velocity. So the subject of today's video is a car moving down a roughly straight road, and the car moves down the video's frame from left to right for exactly 25 seconds. The car's length, which is 4.81 meters, was used as the calibration stick in the Tracker software, and the origin of the axis was set at the approximate center of the car's mass, so that the Tracker software's first point would be located very close to the origin. And we're going to pull up that Tracker video. As you can see in the Tracker video, what the software does is plot the position of the center of mass of the object at each frame of the video, and then take these values and put them both in a chart and in two graphs over on this right side. It's important to note that there is fluctuation in the Y position of the car. However, this is due to inaccuracies in the Tracker software, not the car's actual motion. Moving back over to the PowerPoint, the what-if question asks us about the axes we used for the Tracker software. The car travels along the positive x-axis, a left to right motion. However, the axis is slightly tilted upward to make up for a slight uphill slant in the road. If we were to flip these axes, having, say, the negative x-axis running this way and the positive x-axis this way, the car would obviously have a negative velocity. However, its speed would remain unchanged. This is the absolute value. Next, we have a few quick calculations. We calculate the average velocity vector, which is the final position, which is at the end of the video, minus the initial position at the beginning of the video, divided by the total time of the video, which gives us a velocity of 4.2 meters per second, or approximately 9.4 miles per hour, which is interesting to note because our goal was to stay roughly under 10 miles per hour during the filming. We also calculate the velocity from frame 1 to frame 2, which is equivalent to 3.3, and this is just worth noting now because it's important later on in the video. However, it does indicate that there may be some acceleration or deceleration occurring during the video, that the object is not moving at an actual constant velocity. Here we have a position versus time graph of the Tracker data. As you can see, it's fairly linear. There's a few discrepancies here and there between points, but in general, it's very linear, as shown by our linear regression R-squared value of 0.993, and this indicates that the car is moving at a constant velocity because there's a strong correlation between the time passed and the horizontal position. The second part of the lab consisted of running a code that modeled the motion of the car. Here's the code itself. If we scroll back up here to the top, there's not a whole lot different from my code and everyone else's. However, it's important to note that the range needed to be increased to compensate for the larger size of the car. The car's mass was 945 kilograms. Here's the initial position vector and velocity vectors. The delta t is 0.01 seconds. Total time was roughly 0.835 seconds. And here you have Newton's second law written out in code. Of course, the net force vector is going to be 0, 0, 0, since our object is at constant velocity. And we'll run this code really quickly, just so you guys can see that it works. This first part is a model of the car with a ball traveling along the horizontal axis, and then here you have a graph that looks very similar to the Excel data with the position versus time graph. Close this. Other lines of the code, these optional ones that are currently marked out, save the values calculated by the code in a CSV file, which we can then look at in an Excel plot. Here we have the Tracker data versus the code data, and then both are graphed here. As you can see, there's a slight discrepancy because the code data uses a velocity of 3.3 meters per second, which is less than the average velocity. So the code data estimates that the car moves less than the actual Tracker video indicates. Move back over to our PowerPoint. We have a final slide, which is relating all of this back to Newton's second law. It's very important for us to note that all of these predictions to be accurate, the net force of the car is assumed to be 0. Here we have Newton's second law written out in words. You saw it before in code. Final velocity equals initial velocity plus F net divided by mass times delta t. And what does it all mean? We're looking at a case where the total net force on our system by the surroundings is assumed to be 0. In reality, we couldn't calculate all of the forces acting on a car while it's driving. You have a ton of forces between gravitational forces, friction forces, forces between the engine and the wheels and the axles. But we assume it's all zero because for the initial velocity to be equal to the final velocity, force has to be zero, because obviously we have a change in time and we have a mass. And that's the big picture of the entire lab, is that when the force is equal to zero, your initial velocity is equal to your final velocity. Thanks for watching, guys, and I'll see you next.